students, and welcome back to Study Room. So as I had promised in the last video, I am going to do a quick revision of the chapter Magnetic Effects of Electric Current. Okay, let's go. So before I start, my piece of advice to you will be make sure that you are thorough with all of the topics that you have done in this chapter, that we have covered together in this chapter, because in this revision, I am just going to cover the main points quickly. I am not going to teach it to you in detail, the detail that you would actually need to understand it completely. So make sure you remember and you are thorough with all of the concepts that we have done till now. Okay, let's go. Okay, so what does the first point say? The first point says that a compass needle is a small magnet. Its one end is called the North Pole and the other end is called the South Pole. Now, before this, you had learned that there is this object which is known as a magnet, which has a North Pole and a South Pole. Then we learned that there are these lines, which we later learned that are magnetic field lines, which outside the magnet go from North to South Pole, and inside the magnet they go from South Pole to North Pole. Then the second thing you learned was about this compass needle, and you learned that this compass needle that you see, that sailors use to navigate, you must have seen in movies or books, this kind of a needle this compass has, which points in the north-south direction, and usually this north half of the needle's half that points towards the north is usually red colored, and the half that points towards south is usually white. So how is this needle able to tell you the north and south direction? It is because this compass needle itself is actually a magnet, and what it does is this magnet aligns itself according to the magnetic or the magnet of the earth. So that is why we have a north pole on our earth, we have a south pole. That is because our earth actually acts like a big magnet. It's almost as if a bar magnet is placed inside the earth. That's how you can imagine it. So what does this compass needle do? This compass needle just aligns itself, and what is the reference that it is aligning itself to? The earth's magnet is what it's aligning itself to. Okay, so that tells you that this compass needle in itself is actually a small magnet. It also has a north pole and a south pole. Okay, then we saw that the second point I'm reading, a magnet field exists in the region surrounding a magnet in which the force of the magnet can be detected, right? And how did we represent that magnetic field? We represented the magnetic field in the form of magnetic field lines, right? Right now, I'm just taking the concept of a bar magnet because it is the simplest, right? So here we saw that like this, your magnetic field lines keep getting more and more farther from each other as you go away from the magnet, right? You saw that. Why is that? Let me just make the whole figure and then I will explain it. So now you tell me the direction. Which direction is this line in? Pointing towards the right or pointing towards the left? Pointing towards the right, because it is from north to south outside the magnet, and inside if you want to show one line it will be south to north, but you can avoid showing this line. You can just have this for your reference, and then outside it is the entry point. We know south pole is the entry and north pole is the exit, right? So all of the magnetic field lines seem to be coming into the south pole. Now, what is this saying? The magnetic field exists in the region around the magnet. So this north and south, this rectangular piece, it's actually a cuboid. It's not a 2D figure, it's a 3D figure, right? So this magnet exerts its magnetic strength or the magnetic field around it. Like I had told you, if I am stretching my arms out and I'm like rotating in a circle, so the area that my arms can cover, if I'm a magnet, the area that my arms can cover while I'm rotating is my magnetic field. And I told you that if someone is a little out of my reach, I might be able to touch them, but it will be difficult. So what does that mean? That my reach or my magnetic field keeps getting lesser and lesser as it goes away from me, right? It becomes lesser, it becomes more difficult to exert my influence on someone who is far away from me. Whereas someone who is standing close to me, I can just hit them with my hand, right? That will be fun also. No, don't hit anyone. Okay, so that means that near the magnet, nearer to magnetic field is stronger, right? So magnetic force is more. This force is the magnetic force. And as we go farther from the magnet, strength of magnetic field keeps decreasing. Right? So this means that as close as you are to the magnet, it would be even more easier for the magnet to attract you. That is why if you keep a stapler pin very close to a magnet, it would immediately attract the stapler pin and the stapler pin sticks to the magnet. But if the stapler pin is at a great distance, even if the magnet is exerting its magnetic field, it cannot reach out and grab or pull the stapler pin closer to it. So that means that nearer to the magnet, the force is more, and as we go farther from the magnet, the magnetic force and the magnetic field becomes lesser. The second thing that we learned, do you remember about magnetic field lines? Can you see here the gap between the magnetic field is increasing? What does that mean? When gap is more, if gap is more, field weaker, which means if the gap between the magnetic field lines is very great, that means the magnetic field is very weak. Whereas look at this region near the south pole and near the north pole, how close are the magnetic field lines? They are very close to each other. So in these regions, that means, where do I write it? I'll just draw a line. That means in these two regions, magnetic field lines are close, so field is stronger, right? So that now you remember the properties of magnetic field lines also, except for that they are the close continuous curve, they never intersect each other. This was one very important property that we learned, that if the magnetic field lines are closer together, field is stronger. If they are farther from each other, the field is weaker. Okay, let's go. Moving forward, the third point says that the field lines are used to represent a magnetic field. We have already done that. I've just done it in the revision 2. Then it says that a field line is the path along which a hypothetical free north pole would tend to move. Now, what does this mean? This means that, do you remember this figure that we made when I was explaining field lines to you? I made this figure that if this is the field line from north to south, that means if we keep a compass needle at every point here, it would actually be in a way that the north pole is pointing along the magnetic field line. Does that make sense to you? I'll just repeat my point, but I'll make the figure first so that it is more clear to you. Okay. Just one more. Okay, now look at these compass needles, and I told you that the shaded path is the north pole and the south pole of the compass needle. This is the north and the south of the compass needle. The half that is shaded is the north pole of the compass needle, and the non-shaded half is the south pole. Now look here. What happened? This is something that was observed experimentally. I am not telling this to you. I didn't dream about this. This was seen experimentally, that when a compass needle is kept near any of any area surrounding the bar magnet, how this experiment was conducted was, first 1, 2, 3, 4 and 5. So let's say there are 5 positions of this compass. This is just one compass needle. So what they did was, the experimentalists who were trying to study the magnetic field, what they did was, they kept this compass needle at point 1. Okay, they kept it at point 1 and they noted down the position of the north pointing of the compass needle. So I am not telling you this. I didn't just dream about it. This was experimentally seen. So what the experimentalists did was that they took this bar magnet. Okay. Then they kept this compass needle here and then they noted down the position at towards which the north of this needle is pointing. So I noted down this position. Okay. Then I removed the compass. This is just one compass. It's not 5 compasses here. This is one compass at different positions. Then what did I do? Say I kept my compass needle here. Then they saw that the compass needle was pointing in this direction. So again they noted down the position of the north. Okay. They removed it from here. Then they kept the compass here. Then they saw that the needle is pointing like this. So again they noted down which direction the north pole of the needle is pointing in, and so on. They kept that compass needle everywhere around this magnet, and they saw that the north of the compass needle was pointing in directions like this. Then when they completed, they did the join the dots that everyone has been doing since pre-primary, they found out that this was the shape of the line that was formed in case of a bar magnet. Right? So do you understand what this point means now? That a field line is the path along which a north pole would tend to move. What did we do in this experiment? We noted down the direction in which the north pole is pointing at each point, and then we joined it. So to say, if the north pole was like a car, or if the magnet was like a car, the north pole was want to go along this line, right? Because these dots represented the directions in which the north pole was pointing, right? So that is what it means by the path along which the north pole would tend to move. And you remember this figure we had made, and this is how the experimentalists determined the shape of the magnetic field lines around a bar magnet, and so on. It could also be because of a straight current carrying conductor. They did the same thing, kept the compass needle at each and every point around the conductor, noted down the made points, noted down the direction of the north pole, and then they connected these lines. Okay, great. Now let's look at the next point. So it says that the direction of the magnetic field at a point is given by the direction that a north pole placed at that point would take. This is exactly what I explained to you here, that the experimentalists kept the compasses, one compass, one at a time at each of these positions. The experimentalists kept a compass at each of these positions one at a time, and they just made a dot where the north is pointing, and then they joined the dots. So that is why we are saying that it is the direction that a north pole, or the how did we determine the north pole? We determined by the north pole of the compass, because the compass needle is very easy to move. It moves easily and we can note it down easily. So the north that a compass would take. Okay, great. The next point says that field lines are shown closer together where the magnetic field is greater. This we have already seen. The area near the poles, near the north and south pole, the field lines are like this, very crowded together. And as we go far from the magnet, they become more and more and more spaced from each other. That means the magnetic field is decreasing, or the intensity or the strength of the magnetic field is decreasing. Okay, great. Let's move on. Then it says that a metallic wire carrying an electric current has an associated magnetic field with it. So what does that mean? Do you remember this wire that we had taken and we had passed it through this hole? We had passed it through this hole like this. And what had we observed? We had observed that the magnetic field lines were formed as form of concentric circles with the wire in the middle. Then it says that the pattern of the magnetic field around the conductor due to an electric current flowing through it depends on the shape of the conductor. What are we saying? Here, this is a straight conductor. If you remember, we did in the form of a loop. When we bent this conductor in the form of a loop, we saw that depending on the direction of current, that's why I'm not making the direction of magnetic field lines right now, because we don't know which direction the current is flowing in. So the magnetic field was formed like this, right? And we had one main line flowing here because we saw that the magnetic field due to each of these ends, these points, this point A, and this point B in the middle, they all combined and went into the same direction just at the middle of these points, right? And when we saw that this was bent in the form of a solenoid, when this wire was coiled in the form of a solenoid, it acted like a bar magnet. We saw that the magnetic field lines formed were like a bar magnet. That means they went like this, they went like this, and so on. So the magnetic field lines around that current carrying conductor depends upon its shape. And we learned how can we determine the direction of magnetic field by the right hand thumb rule. If we point the direction of flow of current in our direction of thumb, then the direction which my fingers are curling in, whether it is clockwise or anti-clockwise, that is the direction of my magnetic field. So you have to look at what direction your fingertips are going in, okay, and you have to determine if it's clockwise, anti-clockwise, or if the coil is on the plane or like on a table, then it can also be like coming out of the table or going into the table. Okay, great. What does the next point say? The next point says that an electromagnet consists of a core of soft iron wrapped around a coil of insulated copper wire. So if you remember, we had studied that inside a solenoid, because inside a solenoid the magnetic field lines are super close to each other and parallel. So they are close and parallel. So what do they form? They actually form a uniform magnetic field. Right? We have a uniform magnetic field inside the solenoid. So this uniform magnetic field, it is so strong. It is also found inside a bar magnet, but because the bar magnet is solid, we can't put anything inside a bar magnet. But the solenoid has space in between, right? It's hollow, right? This area is hollow, so you can actually put something in this space. So this solenoid, when some magnetic material such as soft iron, this soft iron is a magnetic material. When a magnetic material is put inside this solenoid, what happens is that soft iron starts acting like a magnet too. And this setup, this whole setup, this solenoid plus this soft iron which is put into its middle, this is known as the soft iron core. Core is anything that is in the middle, right? We know the earth's core is right in the middle of the earth. So soft iron core, because this soft iron is put into the middle of the solenoid. So this soft iron core with this solenoid is the setup for an electromagnet, and it actually produces a very strong magnetic field. The advantage is strong magnetic field, along with what? We can control, very bad, I didn't write it nicely. We can control the strength and also switch the magnet on and off. How? How can we control the strength? We know that in case of this solenoid, the magnetic field strength is dependent upon the current that flows through it, right? So if we increase the current, that means if we increase the voltage of the battery that it is connected to, you know, right? This solenoid is actually connected to a battery. So if we increase the voltage of this battery, the current in the solenoid will increase and the magnetic field related to the solenoid will increase, and the soft iron core gets even more magnetized, and the magnet produced is super strong. And how can we switch it on or off? Just switch off the current in it. As soon as you switch off the current, the magnetic field is gone, right? Because here it's not like a bar magnet. A bar magnet is permanently a magnet. It cannot ever like switch off its magnetic field unless it's like damaged or something, then the magnetic field will be affected. But here, just by switching the key on or off, or just by breaking the circuit, we can switch the magnet on or off in case of an electromagnet. Okay, great. Let's move on. The next point says that a current carrying conductor, when placed in a magnetic field, experiences a force. This is the basis of an electric motor. This is the principle of an electric motor. And how do we determine the direction of each? First of all, this conductor has to be perpendicular to magnetic field. We saw that, and we saw that we Find out the directions using the left hand rule, Fleming's left hand rule. In this case, the middle finger gives the current, the index finger gives the direction of magnetic field, and the thumb finally gives the direction of force. So in this, we were converting electrical energy to mechanical energy. What does that mean? If we are giving electrical energy, that means we are giving the electricity. So how was the setup for this? The setup was North Pole, South Pole. There was this coil, right? We had split rings. So we had this axle or the cylindrical thing which we called the axle. We had split rings P and Q, which these coil ends were attached to. We had brushes and we had the R1 and R2, right? We had the R1 and R2, which were the stationary brushes, and this was connected to a battery. So here what was happening? We were providing the electrical energy. That means we are providing the current. And then according to the direction of current, we used the Fleming's left hand rule to calculate the direction of force. Why? Because we also know the direction of magnetic field, north to south. So we know current direction, we know magnetic field direction, we can find out the force. And why do we say we generate the mechanical energy? Because of the current and the magnetic field, the coil moves itself. We are not moving the coil moves itself. That means when there is any kind of movement involved, so that is mechanical energy. So are we moving the coil? No, the coil is moving itself. We are giving the electrical energy. We are giving the battery. So we are giving the electrical energy and mechanical energy is being produced. Okay, that is the electric motor. Now, in case of generator, what was that? The phenomenon of electromagnetic induction is the production of induced current in a coil placed in a region where the magnetic field changes with time. So you remember when I told you about the two experiments conducted by Michael Faraday? When a coil and the battery was moved closer to the coil, only when there was a movement, there was a deflection in the coil, momentary, just for a second. As soon as the movement of the bar magnet stops, the magnetic field stops, or there is no deflection in the galvanometer. Second experiment was two coils, one connected to the battery, the primary coil, and one connected to the galvanometer. As soon as you put the key in, that means as soon as current flows, just for a second, deflection in the galvanometer. As soon as you stop the current, that means as soon as you take the key out or break the circuit, 1 second deflection in galvanometer, but then galvanometer is at 0. So what does that mean? That there is a current only because of the changing magnetic field around that conductor or any wire. There is no current through the wire originally. The current is being induced, and before that potential difference is being induced, right? The actual thing that gets induced is the potential difference, and because of the induced potential difference, an induced current flows. Okay, and the setup for that was North Pole, South Pole, obviously the battery. We had our coil ABCD. Here there were the rings. We had full rings, right? Let me make it bigger. We had ring 1, which this side was connected to. And we had the second ring, which the other end of the coil was connected to. I'm not making it properly. I'm just doing it in rough. That's why. Okay, this is a revision. Then this was the ring. This was the stationary brush B1 and stationary brush B2. And here are the brushes connected to a battery? No. Why? Because here the opposite thing is happening. Mechanical energy is being converted to electrical energy. That means what are we giving? We are giving the mechanical energy. Mechanical energy means anything to do with movement. So what are we doing? We are moving the coil externally using that axle. How we move that? That is not something you have to worry about. You just have to know that we move the coil. And what happens? Because this coil starts rotating, that means it is making a different angle with the magnetic field every second that it is changing. So that means the magnetic field related to it is changing continuously, right? So because of that, what happens? Current is induced. And how do we find that out? Fleming's right hand rule. In this, what did each finger stand for? This was, here it was current, but here is it the normal current? This is the induced current. In this was the magnetic field. Here also this is the magnetic field. So here in left hand rule, what did the thumb stand for? It was the force. And in right hand rule, we don't say force, we say movement of the conductor. Why? Because if we say force on the conductor, it seems like the force is being exerted on the conductor. But no force is being exerted on the conductor externally. We are doing it. We are moving the conductor voluntarily in the magnetic field so that a current is induced. So this stands for the movement of conductor. Okay, so that is the electric generator because electricity is generated here. Okay, great. Let's move on. The next thing here says that in our houses we receive AC electrical power of 220 volts with a frequency of 50 hertz. This is something that is factual and you have to know about. And you saw that this 220 volts was the difference, potential difference between the live wire and the neutral wire, right? Then it says one of the wires is red insulation called the live wire or positive. The other one with the black insulation is the neutral wire or negative. Okay, it has a black insulation. The third is the earth wire, which is to protect our lives so that if there is any leakage in any appliance, that wire quickly takes up all that leakage, that extra current or the leakage in the current or extra charges, and it takes it deep into the surface of the earth on a metal plate. So it basically earths all of the charges. This process is known as earthing because the earth is electrically neutral. It has a potential of 0. So no matter how many charges come into the earth, no one is going to get a shock from it, or it is not going to affect the earth in any way. But when we do this earthing, it actually saves us from that electric shock that we might have had because of that building current or the leakage of current. Okay, it has a green insulation and it is connected to a metallic body deep inside the earth. We know that now. Great. Let's move on. Now it says that the fuse is the most important safety device used for protecting the circuits due to short circuiting or overloading. And we had studied short circuiting and overloading. What it was, overloading is when the live and the neutral wire come in contact. And why will that happen? They normally don't come in contact because they have this insulation. They have like a coating on them so that they don't come in contact. If the insulation or the coating gets damaged, they come in contact, and what happens? There is a huge spike in the current which is known as short circuiting. Okay, and we learned some ways to avoid overloading, like switching off a plug when we are not using it, not using an adapter so that not a lot of devices are connected to just a specific switch or a specific plug, just one plug, right? And a few other points. So students, this brings us to the end of this chapter. We have studied a lot of interesting things in this chapter, going from the magnetic field generated because of a current which we never knew about, which Hans Christian Oersted accidentally discovered. That's why we have this beautiful phenomenon to study. Then we saw how the magnetic field is in case of a straight wire, in case of a loop, in case of a solenoid. Then we studied about electromagnetic induction and the generator. Before that, we studied about the motor, and we did a lot of properties of the magnet as well. So make sure you know all of these topics thoroughly, because this is a very interesting chapter and it is actually very scoring also, because once you've understood the concepts, it is very easy to apply them. Okay, so make sure you do it all very nicely. I hope you enjoyed this chapter, students. Thank you and take care.